Now we are going to discuss essential concepts related to level of service. Although speed is a major concern of the motorist using a freeway facility, it remains nearly constant over a wide range of flows. Freedom to maneuver within the traffic stream and proximity to other vehicles are equally important and are used in preference over speed in describing the level of service. Besides, density increases throughout the range of flows up to capacity and therefore provides a better measure of effectiveness. The densities used to define levels of service for basic freeway sections are as follows. So A is the highest level of service and F is the lowest level, and associated density ranges are mentioned over here in passenger car per mile per lane. Level of service criteria for basic freeway segments are shown in Table 7-1. To be within a given level of service, the density criterion must be met. Figure 7-3 illustrates the relationship among speed, flow, and density for basic freeway segments operating under base conditions. Various levels of service are shown using density boundary values. Either Table 7-1 or Figure 7-3 may be used in making level of service determination. So look at the Table 7-1 LOS level of service criteria for basic freeway segments. So here you can see A, B, C, D and E level of services, and you can see this part of the table is meant for free flow speed equal to 75 miles per hour, and this one is meant for 70 miles per hour, and so on. You can see the speeds are mentioned, and here for every free flow speed you can see here maximum density in passenger car per mile per lane, maximum speed in miles, minimum speed in miles per hour, and a maximum V over C ratio. And remember that V over C means volume to capacity ratio, and this is the maximum service flow rate, and that is again in passenger car per hour per lane. So you can see that as this ratio V over C is increasing, so you can see that we are moving from level A to level E. Well, this is the figure 7-3, and basically it's showing the relationship between the average passenger car speed, density and the flow rate, and you can see here 55 miles per hour, 60 miles per hour, 65 miles per hour, 70 miles per hour, and this is the special case that we can consider in the case of rural areas where 75 miles per hour. So you can see that 55 miles per hour speed can be maintained up to flow rate of 1750. 60 miles per hour can be maintained up to 1600. 65 miles per hour can be maintained up to 1450 flow rate, and 70 miles per hour it can be maintained up to 1300. So if we consider these speeds from 55 to 70 miles per hour that we generally consider for the urban roads, so you can see that up to 1300 flow rate, that is passenger car per hour per lane, you could be able to maintain the specific speeds. Now look at the various level of services. Level of service A. Free flow operation. Free flow speeds prevail. Vehicles completely unimpeded in their ability to maneuver within the traffic stream. Average spacing of 528 feet. The effects of incidents are local and minimal. So this is the highest level of service. Then LOSB, reasonably free flow, generally free flow speed, ability to maneuver within the traffic stream slightly restricted, average spacing 330 feet. The effects of minor incidents and point breakdowns are still easily absorbed. Then comes level of service C, provides flow with speeds still at or near free flow speed, freedom to maneuver within the traffic stream noticeably restricted, and lane changes require more care and vigilance by the driver. Average spacing 220 feet. Local deterioration due to incidents is substantial, and queues may be expected to form behind any significant blockade. Minor incidents may still be absorbed. Then level of service D, speeds begin to decline slightly with increasing flow. Density begins to increase somewhat quickly. Freedom to maneuver is more noticeably limited. Average spacing 165 feet. Minor incidents can be expected to cause queuing. LOSE describes operation at capacity at its highest density values. So this is very important that LOSE, level of service E, describes operation at capacity at its highest density values. Operations are volatile and virtually no usable gaps exist in the traffic stream. Maneuverability within the traffic stream is extremely limited. Average spacing 110 feet at speeds still over 49 miles per hour. Any incident can be expected to produce a serious breakdown with extensive queuing. The level of physical and psychological comfort afforded driver is poor. Any disruption of traffic streams such as vehicles entering from a ramp or a vehicle changing lanes can establish a disruption wave that propagates throughout the upstream traffic flow. And this is the worst level. Level of service F describes breakdowns in vehicular flow at points of recurring congestion such as merge, weave, or lane drop locations. It can also be caused by traffic incidents. In all cases, breakdowns occur when the ratio of arrival flow rate to actual capacity exceeds 1. Level of service F, operations within a queue are the result of a breakdown or bottleneck at a downstream point. So level of service F also describes condition at the point of breakdown or bottleneck and the queue discharge flow that occurs at speeds less than 50 miles per hour. Whenever LOSF conditions exist, there is a potential to extend upstream queues for significant distances. Determination of level of service for a basic freeway section generally involves three components. Number 1, flow rate. Number 2, free flow speed. And number 3, level of service. An equivalent passenger car flow is rate An equivalent passenger car flow rate is calculated using equation 1 to allow for the effect of heavy vehicles and variation of traffic flow during the hour in the traffic stream. So you could be able to see that equation on the next slide. So this is the equation 1. So V sub P is equal to V divided by these things PHF and F sub HV and F sub P. And here you can see that V sub P, that is the 15-minute passenger car flow rate in passenger car per hour per lane units. So it is in fact the peak 15-minute passenger car flow rate in these units. V, that is the hourly volume in vehicles per hour, PHF peak hour factor, and the number of lanes, FHV heavy vehicle adjustment factor, and F sub P, that is the driver population factor. Observations of traffic flow consistently indicate that the flow rates found in the peak 15 minutes period within an hour are not sustained over the entire hour. The peak hour factor in equation 1 accounts for this phenomenon. On freeways, typical peak hour factors range from 0.8 to 0.95. Lower peak hour factors are characteristics of rural freeways or off-peak conditions. Higher factors are typically of urban and suburban peak hour conditions. If local data are unavailable, 0.88 and 0.92 may be used for rural and urban suburban peak hour conditions respectively. Freeway traffic volumes that include a mix of vehicle types must be adjusted to an equivalent flow rate expressed in passenger car per hour per lane. Adjustments for the presence of heavy vehicles in the traffic stream apply for trucks, buses, and recreational vehicles, or you can say RVs. Trucks and buses are treated identically. So this point must be noted that trucks and buses are treated identically. A two-step process is used to determine F sub HV, the passenger car equivalent of each truck or bus, that is E sub T, and recreational vehicle E sub R is found for the traffic and roadway condition under study. So you can say that E sub T, this is a passenger car equivalent of each truck or bus, and E sub R, that is the passenger car equivalent of each recreational vehicle. Using the value of E sub T and E sub R and the proportion of each type of vehicle in the traffic stream, P sub T and P sub R, the adjustment factor F sub HV may be computed. So here P sub T and P sub R. P sub T is the proportion of truck or buses, and this is P sub R, that is the proportion of recreational vehicles. The impact of heavy vehicles on traffic flow depends on grade, conditions as well as traffic composition. Passenger car equivalents can be selected for one of three conditions. Number 1. Extended freeway segments. It is often appropriate to consider an extended length of freeway containing a number of upgrades, downgrades, and level segments as a single uniform segment. As a rule, extended segments can be used where no one grade of 3% or greater is longer than 0.25 mile, or where no one grade of less than 3% is longer than 0.5 mile. Extended general freeway segments are further classified into level, rolling, and mountainous terrain. And I'm sure that these classes, level, rolling and mountainous terrains, are not the new one for you. Level terrain includes short grades of no more than 2%. Rolling terrain causes heavy vehicles to reduce their speed substantially below those of passenger cars, but not to crawl speeds for any significant length of the time, which typifies mountainous terrain. Refer to Table 7-2 for values of E sub t and E sub r for extended freeway segments. So this is the Table 7-2 passenger car equivalents on extended freeway segments. So you can see E sub t, that is meant for trucks and buses, and E sub r, that is for recreational vehicles. And this column is for level terrain, this is for the rolling, and this is for mountainous. So in this way you can pick the corresponding value of E sub t and E sub r. Number 2, specific grades. Any grade less than 3% and longer than 0.5 mile, or any grade of 3% or more and longer than 0.25 mile is usually analyzed as a separate segment. Tables 7-3 and 7-4 give values of E sub t and E sub r for specific upgrade sections. Procedures adopt passenger car equivalents that are calibrated for a mix of trucks and buses, which have a weight to power ratio of between 125 and 150 pound per horsepower. Typical weight to power ratios of recreational vehicles range from 30 to 60 pound per horsepower. So this is the table 7-3 passenger car equivalents for trucks and buses on upgrades. So here different upgrades have been considered, the length of the sections, and here you are having the percentage of truck and buses, this row, and you can get the value corresponding to the percentage of trucks and buses, length of the section, and the upgrade, that is in percentage. So in this way we can get the value of the passenger car equivalents for trucks and buses on upgrades. Well, if you just look at this table, table 7-4, passenger car equivalents for recreational vehicles on upgrades. So this column is for upgrade in percentages, length of the section, and here percentage of RVs, and here you are having the value. So in this way we can get the value of E sub r. This is the table 7-5, passenger car equivalents for trucks and buses on downgrades. So downgrades are mentioned, length of the section, and this is meant for the percentage of the trucks. So in this way we can get the value of E sub t on downgrades. Well, number 3, there are few specific data on the effect of heavy vehicles on traffic flow on downgrades. In general, if the downgrade is not so severe as to cause trucks to shift into low gear, they may be treated as level terrain segments. Where more severe downgrades occur, Table 7-5 gives guidelines for use in selecting downgrade values of E sub t. Well, this point is important, that for recreational vehicles, downgrades may be treated as level terrain. Okay, now consider this point. If there is a continuous series of grades in the freeway alignment. An average grade to the point in question can be used. This average grade is computed from dividing the total rise in feet from the beginning of the composite grade by the length of the grade in feet. The average grade technique is acceptable for grades in which all subsections are less than 4% or the total length of the composite grade is less than 4,000 feet. For more severe composite grades, Highway Capacity Manual (HCM) provides a detailed technique which is based on the vehicle performance curves and equivalent speeds. The adjustment factor F sub HV for heavy vehicles are computed using the following equation. Now look at this equation. This is FHV, that is equal to this, and FHV, that is the heavy vehicle adjustment factor, E sub T, E sub R. These are passenger car equivalent for trucks and buses. This is E sub T. And E sub R is the passenger car equivalent for recreational vehicles in the traffic stream. P sub T, P sub R, proportion of trucks and buses and RVs in the traffic stream respectively. So this P sub T is meant for trucks and buses and P sub R is meant for recreational vehicles. In many cases where recreational vehicles represent a small percentage, it may be convenient to consider all heavy vehicles as typical trucks. Thus, a traffic stream consisting of 14% trucks, 3% recreational vehicles, and 1% buses might be analyzed as 18% truck. It is generally acceptable to do this where the percentage of trucks and buses in the traffic stream is at least 5 times the percentage of recreational vehicles present. Determination of free flow speed. The mean speed of passenger car measured under low to moderate flows up to 1300 passenger car per hour per lane is the free flow speed. In this range of flow rates, speeds are virtually constant for a specific segment of freeway. FFS, that is the free flow speed, can be measured directly in the field or estimated using guidelines provided based on the Highway Capacity Manual. For a field measurement, the study should be conducted at a representative location within the section being evaluated. A systematic sample of at least 100 cars across all lanes during off-peak hours could provide a satisfactory measurement. If field measure data are used, no subsequent adjustments are made to the free flow speed as it reflects the net effect of all conditions at the study site. If field measurement of free flow speed is not possible, it can be estimated using the following equation. Well, this is the equation, or you can say the formula meant for free flow speed, and you can see that there are different variables. So look at the equation. BFFS means base free flow speed, and that's 70 miles per hour for urban areas and 75 miles per hour for rural areas. FLV, F sub LV, F sub LW, adjustment for lane width from table 7-6. F sub LC, adjustment for right shoulder lateral clearance for table 7-7. F sub n adjustment for number of lanes from table 7-8, and F sub id, that is adjustment for interchange density for table from table 7-9. So all these, are in the units of miles per hour. Look at that. The base free flow speed 70 or 75 miles per hour is reduced by adjustment factors in table 7-6 to 7-9 as mentioned in the previous slide when roadway conditions differ from base conditions. No adjustment factors are recommended for left shoulder clearance of less than 2 feet. It is considered rare and professional judgment is recommended. Only mainline lanes, both basic and auxiliary, are included in counting the number of lanes. High occupancy vehicle (HOV) lanes should not be included. The adjustments in table 7-8 are based exclusively on data collected on urban and suburban freeways. Rural freeways typically carry 2 lanes in each direction. The value of adjustment for number of lanes F sub n should be 0 in using equation 3 to estimate FFS of a rural freeway. Interchange density is determined over 6-mile segment of freeway, 3 miles upstream and 3 miles downstream, in which the freeway section being studied is located. An interchange is defined as having at least one on-ramp. Look at the table 7-6, adjustments for lane widths. So corresponding to different lanes, we are having the reduction in free flow speed, that is FLW. You can pick the values accordingly. This is table 7-7, adjustments for right shoulder lateral clearance. So based on the right shoulder lateral clearance and the lanes in one direction, you can get the reduction in free flow speed, that is F sub LC in miles per hour, by using these columns. Look at this table 7-8, which is meant for adjustments for number of lanes. So look at that number of lanes, one direction, in one direction, and based upon that you can get the reduction in free flow speed, that is F sub n in miles per hour. And this table 7-9, adjustments for interchange density. So interchange is per mile, this column, and correspondingly we are having the values for reduction in free flow speed, that is F sub id in miles per hour. Determination of level of service. The level of service on a basic freeway section can be determined directly from figure 7-3 using free flow speed and the flow rate. The following steps illustrate the procedure. Well, this is the figure 7-3, and you can see that this portion is level of service A, this is level of service B, this portion, this is the level of service C, and this is the level of service D, and This one is showing the level of service E. So if your point is lying in these different segments, so you can get the level of service very easily. Number 1, define and segment the freeway section as appropriate. Number 2, on the basis of measured or estimated free flow speed, construct a typical curve as shown in figure 7-3. The curve should intersect the y-axis at the free flow speed. Number 3 step, enter the flow rate V sub P on the horizontal axis. The horizontal axis is representing basically V sub P. So enter the flow rate V sub P on the horizontal axis and read up to the curve identified in step 2 and determine the average passenger car speed and level of service corresponding to that point. Determine the density of flow as follows. D is equal to V sub P over S sub PC, and here D means the density in passenger car per mile per lane, and V sub P, that is the flow rate in passenger car per hour per lane, that is basically the 15-minute flow rate. And if you just look at the S sub PC, that is average passenger car speed in miles per hour. The level of service can also be determined using the density ranges provided in table 7-1. Now you would find 4 solved problems. Look at this 7.1, and the information which is given: service flow, the composition of traffic of heavy vehicles, 6% trucks, 12% buses, 15% recreational vehicles, 67% passenger cars, plus 3% grade for 2 miles, level terrain, lateral obstructions 5 feet from both sides, length 2 miles, lane width is equal to 12 feet, and 1 interchange per mile. So first, considering the case of upgrade, and you can see that P sub T is coming equal to 0.06 plus 0.12, that is 0.18, because 6% the trucks and 12% are buses. So we are getting these in fractions, so you are getting it. And then by consulting table 7-3, we have got E sub T equal to 2. Then look at this recreational vehicles, P sub R, that is the proportion of recreational vehicle, that is 15%, so it is 0.15. And then by consulting table 7-4, we have got E sub R equal to 1.2. Then by using this formula for FHV, and you know F sub HV, that is the heavy vehicle adjustment factor, so just plug in the values and you will be getting the answer equal to 0.826. Then the downgrade, well, you can see that E sub T, that is 1.5 from table 7-5, and you can see that A sub R, that is 1.2, that is from table 7-2, corresponding to the condition level terrain. And FHV, again, by using the formula, we have got 0.893. Now for the part B, assume peak hour factor equal to 0.9, that is meant for urban or suburban conditions, and the number of lanes on one side 4 and the total lanes are 8. So upgrade in that particular case, V sub P, that is 15-minute passenger car flow rate, that can be determined by using this formula. So by plugging the values, we have got the V sub P, that is 1009 passenger car per hour per lane. Now considering the downgrade, so V sub P, that is using the same formula, but obviously you are having a different value of F sub HV over here, so you are getting the answer 933 passenger car per hour per lane. Then from table 7-6, 7-7, 7-8 and 7-9, we can get these factors, F sub LW, then you can see F sub LC, F sub N and F sub ID, and then free flow speed can be determined by using the formula, and then it is the 65.8 miles per hour. So by consulting figure 7-3, the existing upgrade level of service is coming B, and by using figure 7-3 again, existing downgrade level of service is again B. At capacity, level of service E, because in that particular case V sub P is 2360 passenger car per hour per lane. So by consulting figure 7-3, you can get V sub P corresponding to level of service at capacity. You can say it is 2360. You can get it from figure 7-3, and from that obviously the level of service is E. And then using the formula again, and here V is equal to Vp into VHF multiplied by N multiplied by FHV. So basically this is this formula we have used for V, and this V that is hourly volume, that is in vehicles per hour. So just by using this for upgrade case and the downgrade, so maximum service flow corresponding to level of service E, that is coming equal to 7018 vehicles per hour, and in the case of downgrade, maximum service flow corresponding to level of service E, that is coming 7587 vehicles per hour. Well, problem 7.2, peak hour factor is given, lane width, full shoulder outside, rolling terrain, extended section, 6% trucks, 1.5 interchanges per mile. So it means the proportion of truck, that is 6% of 0.06, and considering the rolling terrain and consulting table 7-2, we can get E sub T 2.5. Then look at the formula for F sub H V, and F sub H V, that is heavy vehicle adjustment factor. This is the formula for that, but as the recreational vehicles are not present, so this part will not be used. Just plug in the value, the answer is coming 0.917. If we consider the level terrain, then this E sub T is 1.5, so the answer is 0.97. But here in this problem, obviously we are going to consider the rolling terrain, so this value will be employed. Then look at these factors, F sub LW, F sub LC, F sub N and F sub ID. So by consulting table 7-6, 7-7 and 7-8 and 7-9, we have got these values. So just plug in the values in the formula of free flow speed, and we are getting it 63.5 miles per hour. So if we just develop uh, a curve corresponding to 63.5 miles per hour on figure 7-3, so corresponding to uh, level of service B, the maximum flow rate. So the maximum flow rate for level of service B, that is coming from the figure 7-3, 1143 passenger car per hour per lane, and the maximum flow rate level of service D, that is coming 2069 passenger car per hour per lane, again by consulting figure 7-3. And then by using these V15, V sub P, this is basically 15-minute passenger car flow rate. So use this formula, and in this way you can get the maximum service flow corresponding to B level of service, and that is coming 3983 vehicles per hour, and the maximum service flow corresponding to level of service D, and that is coming 7210 vehicles per hour. Now look at the problem 7.3. AADT is given, that is average annual daily traffic. K factor is given 0.10. D, that is directional factor, that is also given, that is 0.55. 10% buses, 5% recreational vehicles, 10% trucks, peak hour factor 0.9, level terrain extended section, no lateral obstructions, design standard LOS level of service D, estimated free flow speed, that is 65 miles per hour. So obviously we will have to use this formula, and if you just recall this DDHV, this is directional design hour volume. AADT, that is average annual daily traffic, and this K is the factor, and D is the directional factor. So just plug in the values, you are getting the answer DDHV equal to 4510 vehicles per hour. And then you can see that P sub T, that is the proportion of trucks and buses. So 0.1 plus 0.1, because you can see that this answer, that is 0.2. So 0.2 is P sub T, because 10% trucks and 10% buses. So 0.1 plus 0.1, that is 0.2. So by consulting table 7-2, considering the level terrain, so E sub T is coming 1.5. And if you just look at the proportion of recreational vehicle, that is just 5%, so it will be written as 0.05. So E sub R, that is the passenger car equivalent for each recreational vehicle, that is 1.2 from table 7-2. Now here look at that F sub HV, that is heavy vehicle adjustment factor. This is the formula for that. So just plug in the values, and we are getting the answer 0.90. So maximum flow rate level of service D, that is VP, that is 2090 passenger car per hour per lane, again by consulting figure 7-3. And then the formula can be rearranged, and you can write that N, that is the number of lanes, that is equal to V over V sub P, and this is PHF, peak hour factor, and this is F sub HV, and that this is the heavy vehicle adjustment factor. So just plug in the values, the answer is coming 2.66 lanes, so it means 3 lanes are needed. We can solve this question alternatively like that. We know this formula for V sub P. You can write the formula, and if we consider n is equal to 2 in this, you would find V sub P equal to 784, and corresponding to that the level of service is F. For n is equal to 3, V sub P, that is if you just plug in the values, the answer is coming 1856 passenger car per hour per lane, and the level of service is D. And for n is equal to 4, VP is coming 1392 passenger car per hour per lane, and the level of service is C. So obviously in this question the designing is to be done correspond to level of service D, so n, that is the number of lanes needed, are equal to 3. Well, this is problem 7.4. Plus 3% grade for 1 mile. DDHV is given 2500 vehicles per hour. 20% trucks. PHF 0.90. Lane width 12 feet. No lateral obstructions. Both sides. 0.5 interchanges per mile. So first looking at the upgrade. So P sub T, that is 0.2, because you can see that the trucks, 20% trucks are there, and by consulting table 7-3 we are getting E sub T, that is the passenger car equivalent for each truck and buses, that is equal to 1.5. F sub HV, and F sub HV, that is a heavy vehicle adjustment factor. So by using this formula, just plug in the values. So the answer is coming 0.909. Then by consulting table 7-6, 7-7 and 7-8, concerning the rural roads, and table 7-9, we are getting these values equal to 0. So the free flow speed, that is coming equal to 70 miles per hour. So maximum flow rate, level of service B, that is coming equal to 1260 passenger car per hour per lane by using the figure 7-3. Now the number of lanes can be determined by using this formula. So just plug in the values. V is equal to 2500 vehicles per hour, which is given in the question statement, and then V sub P 1260 and PHF 0.9 and F sub HV, that is 0.909, so 2.43 lanes, so obviously 3 lanes needed. Alternatively, by using this formula, you can get V sub P, that is 2500 over 3 into divided by 0.9 divided by 0.909, and the answer is 1019 passenger car per hour per lane. If one of the upgrade lanes is designated as a truck lane, check if still maintaining level of service D. 2500 vehicles per hour into 0.2, that is equal to 500 trucks per hour total. And this Vp over E sub T will give you the number of trucks. V sub P, that is 1260 passenger car per hour per lane, divided by 1.5, so the 840 trucks. So here you would find that the level of service is A. Since there are 500 trucks less than 840 per hour in the traffic stream, with all of them remaining in the climbing lane, level of service A can be maintained in that lane. However, remaining two lanes carry 2500 minus 500, because 500 trucks will be taken by this. So 2500 minus 500, that is 2000 passenger cars per hour. So V sub P, that is equal to 2000 divided by 2 divided by 0.9 divided by 1, that is coming 1111 passenger car per hour per lane. If we consider the downgrade, the same solution will be valid for that. So in this way, in this lecture, we discussed some very important concepts related to level of service, and we have gone through the solved problems. Thank you.